Okay, thanks for coming, everyone. I hope everybody had a great 4th of July. Before we get going, I did want to make one announcement. I just sent out an email as well, but I've been made aware that the quiz, which was due this weekend, wasn't visible to students. So what I've done for this quiz, I think it's good if you still get a chance to go through this quiz. I think it'll help you as you're studying for the second midterm here. What I would like for you to do is to complete it before the due date, which is July 8th. So that is Wednesday. And what I will do is everyone who submits the quiz, I'll give you 10 out of 10. But I think it's important that you actually look at the questions that are on the quiz and think about how they might look like multiple choice questions in the final or in the midterm. So having said that, I guess this review, how we do this review lecture is a little bit up to you. So as I've said, I have a lecture that's here, right? I can give a lecture that sort of gives an overview of the material that we've covered. I've posted that lecture sort of pre-recorded online if you want to look at it. But I also want to give people a chance to kind of have a session where you can ask me, questions that you have about thermodynamics. Right? So I'd like to give time for that first. And then if we kind of exhaust all the questions, then I can start to go through this lecture. But since there's a pre-recorded version of this lecture anyway, I'd like to sort of give people a chance to voice their questions first. So with that, I will turn the floor over to you. So maybe just as a reminder, the topics that we were covering in the exam. So the last exam ended right when we stopped closed systems. So this exam will cover, okay, so here we go. Is there any way to view questions of past quizzes? I believe that there is, so long as you answered the quiz. I think you should be able to go back into the quiz and look at the questions. I think if you didn't answer the quiz, then I think the way that my courses works is that you can't look at the questions. It's always a little tricky for me because as an instructor, the way that it works is not great for me to see what students see. But I think if you have, and I haven't answered any of the quizzes, but I think if you haven't answered a quiz, you should be able to go on it and look to see how you did. I don't know if anyone confirm if that's the case. So just to get back to the topics that we'll cover in the exam. So I believe that we stopped the last exam at the end of open systems and now or closed systems. So now we'll do open systems. So you need to know how to conserve mass, how to draw control volumes, how to do the first law analysis on an open system, how to do a second law analysis on an open system. We talked about Carnot engines. So we sort of defined what a heat engine is, what a refrigeration unit is. We talked about how to get the ideal version of performance out of particular processes, right? So that we have that sigma dot term, which goes to 0. We talked about Carnot efficiencies and Carnot coefficients of performance. We talked also about ideal turbines and pumps and how when we do a second law analysis of those components, if we make a series of assumptions, it turns out that there's no change in specific entropy across ideal turbines and pumps. So that's sort of a way that we can fix a state coming out of an ideal pump. And then we can use the isentropic efficiency, which compares the power, say, generated out of a real turbine in an ideal turbine, or the power consumed by a real pump in an ideal pump. And then that isentropic efficiency tells us that. So you could see a problem where maybe you have enough information to fix the outlet of the real turbine, and then you can use the fact that the ideal turbine is isentropic, so then you could find the ideal outlet, and then you could compare the powers from the real and the ideal turbine and come up with an isentropic efficiency. Or maybe you're given an isentropic efficiency, and then you can use the fact that an ideal turbine is isentropic, so you can find the ideal power, and then you can use the ideal power and the isentropic efficiency to find the real power, which will give you the enthalpy at the exit of the real turbine. And then after that, we started to talk about how we can chain different processes together to form a particular type of heat engine called a Rankine cycle. The Rankine cycle is kind of an important cycle here in the United States and across the world because it's something that we use to generate power if we're getting power by burning coal or by running nuclear power plants. So this is a pretty common cycle that we use in real life to generate power. Now, we talked about if we can do a first and second law analysis on all of the open systems inside a Rankine cycle, then we can find the thermal efficiency, which would be the net power divided by the heat transfer in. Or as I like to think about it, as the energy benefit, in this case net power, divided by the energy cost, which is the fact that we have to do something like burn coal to add heat into the system. So does anyone have questions that they would like to ask, or would people prefer that I just go through the review lecture? Okay, we have one recommendation for the review lecture. Maybe if you would prefer the review lecture, maybe if you can just put your hand up in the in Zoom here. Although I guess the lack of questions is also kind of a vote for the review lecture. So it looks like we're pretty strongly in favor. If you do have a question, please let me know, right? So we will do this, right? So our review here is we're talking about this second exam, which is coming up on Thursday, right? So this will have the same timing as we have for the previous exam. The notice for that is on the website, right? So here, so we talked about what's on the sort of list of topics that we'll go over for this exam, starting with open systems, entropy, and the second law. So how do we find entropy in different cases? How do we use entropy in the second law equation? We talked about the rate equation for open systems. Then we talked about Carnot cycles, whether they're heat engines, heat pumps, or refrigerators. If they're heat engines, we have a thermal efficiency. But if they are refrigerators or heat pumps, then we have a coefficient of performance. We talked about isentropic efficiency. And then we started to talk about Rankine cycles, which is this idea that we can chain different components together to make a heat engine. So kind of at the very base of what we do when we're looking at open systems is this kind of 3 to 4 part process, right? So first we want to draw our control volume. So what defines where our system is, right? Now in an open system, we're typically going to have one or more porous boundaries, right? So boundaries where mass can flow through. Then we'll say what happens to the mass. So we have to know, because in these open systems, the fact that there's mass going through the system is important, right? Because we need to know what's happening to the mass before we can figure out what's going on with the energy. So that'd be the next step in our process. Now we use the rate version of the first law to do that. And then sometimes, particularly if I'm designing something, then we want to say, can this process happen in real life? Right? And the way that we do that is we look at a second law analysis. So again, we have an open system rate equation for the second law. And what we know about the second law is that entropy is always being generated. And that's represented by that sigma dot term. Just before we get going, Austin, I see that your hand is up. Do you have a question? Or I know in Zoom it's sometimes, thank you. I know it's sometimes a pain to put your hand down. So I actually don't know how to do that if I'm on the other side. So thanks. Right. So we talked about after we draw our control volume, we have to do conservation of mass. It's important to know what's going on with the mass. So here we have this first term. This kind of tells us how much mass is being stored in our system over time, right? Or if we take the rate equation, this is the rate at which mass is being stored. Kind of the example that I like is this idea of a cup being out in the rain, and there's some rate at which the level is rising, right? And that's going to be related to the change in volume. And if the density is constant, then that change in volume is related to the rate of the mass increase inside the cup. We can find that by adding up all the mass flow rates that are coming in. In this case, I guess it would be the rate that rain is falling into the cup, minus the rate at which all the mass is flowing out. We could imagine a cup where maybe we poke a hole in the bottom and now it's losing mass as well. So some assumptions that we make, right? And remember, this is common assumptions, which that's okay. Yeah, common assumptions is different than assumptions that we make all the time, right? So certainly in the long answer problems, I might ask you to relax some of these assumptions, right? But if I didn't, assumptions we're used to making, or at least that we can make, are that the system could be at steady state, right? And if it's at steady state, this term here goes to 0. For most of the systems we've looked at, we have one inlet and one outlet, right? So if your system was at steady state with one inlet and one outlet, that would mean, by conservation of mass, that all the mass flow rate that's coming in, you have to have an equal mass flow rate going out. So the velocity might change, the density might change, but the mass flow rate stays the same. Conservation of energy for an open system looks like this. Again, we have this energy storage term. Just like in closed systems, we're interested in heat transfer into our system, right? So this is HIP, heat in is positive. We're interested here in work that happens inside our control volume. So this W.CV term essentially refers to power that's being either consumed or developed by fan blades inside of our system. And then we have some energy term that's related to the mass that's coming into the system, and an energy term that's related to the mass that's leaving the system. So this is just, these next couple slides just say kind of what all these terms are, so I won't repeat that, right? So here, right, we go through all of these, right? And inside these energy terms, there's 3 different terms that we typically concern ourselves with the energy that's coming in and out with the mass. So the first is a specific enthalpy term. Remember, as we were sort of going through the material, this is when we first defined what enthalpy was, that it's the specific internal energy plus this pressure times specific volume term. But since it's kind of a pain to look up both specific internal energy and specific volume, if I knew, say, the temperature and pressure of a superheated vapor, we just define one property, because once we know 2 extensive properties that are independent, we know all of them. So let's combine some of them into this thing called specific enthalpy. We have another term that's related to the kinetic energy coming in and out with the mass, and another term that's related to the potential energy coming in and out with the mass. Now the problem is, right, this class is kind of notorious for unit conversion problems, right? And one of the things that's difficult is when we go, sometimes it's hard enough in metric, right? So in the metric problem, even still, if these kinetic and potential energy terms stick around, the units are probably going to be wrong, right? So here, H, when we look it up in the textbook, is in kilojoules per kilogram. But if we have velocity in meters per second, or height in meters, these 2 terms are going to be in joules per kilogram. So we'd have to divide both of these terms by 1,000. So we write it this way just to get the quantity right, but it's still going to be up to us when we're doing problems to get the units right. And that's harder to do in the imperial system, because what happens here is that even just to get the quantity right, to get to energy per unit mass, we have to divide both of these terms. These same 2 terms, we'd have a problem with the units even in metric, but we have to divide them by this GC, right? Remember, this is something about sort of this common gravitational acceleration, or the gravitational acceleration here on Earth, but the units are funny because we would use this in Newton's second law to get the units right? To get rid of the mass and add a force. So the units there, you got to remember the units of GC. But even when we do that, so if our velocity was in feet per second, or our elevation was in feet, then these would give us foot-pounds per pound mass. And that's good because a foot-pound is a unit of energy, right? It's a force times a distance. But when we look up H, it's in BTU per pound's mass. So if these two things stick around and we have foot-pounds per pound mass, once we do these calculations, then we have to convert those foot-pounds to BTU. And, you might not be trying to remember this, but maybe it'll get burned into your memory. Or if not, I'm pretty sure it's just on the equation sheet. But I think there's like 775 or 778 foot-pounds per BTU, right? So again, it's kind of close to 1,000, but you still have to do some unit conversion if those terms stick around. So basically, the hair on the back of your neck should probably start to stick up any time where you can't neglect kinetic energy or potential energy in the first law equation. It doesn't matter if you're talking about imperial units or in metric units. The units are going to be important in these kinetic and potential energy terms. If we're dealing with the open version of the first law, then some assumptions that we'll often make include that the system is at steady state. So basically all the problems we do in this class, we cancel this out. One inlet, one outlet's pretty common. So if that happens, we lose the summation signs if there's only one inlet and one outlet. Oftentimes, we'll neglect changes in kinetic energy, although this isn't true for things like nozzles and diffusers, where the change in kinetic energy is important. We'll often neglect the change in potential energy. This is usually true, but maybe if you were doing a problem from maybe the top of Niagara Falls to the bottom of Niagara Falls, maybe you would want to include this to see how important that elevation term is. Right? We'll often assume that open system processes are simple processes where it's either the heat transfer rate or the power that matters, but not both. So usually we'll cancel one of those two things out. If we have processes that are chained together, we will typically assume that there are no friction or heat losses in whatever lines we're using to connect our different components. So if you're doing a Rankine cycle and you have mass that's coming out of a turbine, and then eventually it goes into a condenser, we'll assume that the temperature and pressure, for example, are the same coming out of the turbine and going into the condenser. Although there will actually be some losses in the system there, we'll say that those losses are small relative to the other terms that we're calculating, and that'll really cut down the number of states that we have to fix throughout the problem. So if you can do this, right? So one of the things that I talk about in this class is that, you kind of want to follow this 80-20 rule where if there's a way for you to get 80% of the benefit when you're, or maybe 80% of the grades when you're doing a problem in 20% of the time, then that's a pretty good method to use, right? So I think that while the ratio might not quite be 80 and the time might not quite be 20, I think that when you look at these types of problems that we'll see on this exam and moving forward, if you can demonstrate to me that you know how to derive the symbolic solutions for these problems to get equations that you'll use to answer the problems, then you're kind of demonstrating that you know how to do the thermodynamic analysis. And that's important. So I'm always going to recommend to you to start with the whole first law. I know it takes a couple extra seconds to write that down. And on a test, sometimes it can feel like you're trying to save every second you can. But I do think that if you write down that first law and you sort of cross out the different terms, right? Because I'm definitely going to grade you based on your demonstration of knowing how to use the assumptions, right? So if you write down all the right assumptions and then write down that the power developed by the turbine is m dot times delta H, right? Or then I know that you got the right answer, but you have to tell me why you got the right answer. And, I can ask the problem so that that's not how you find the power through a turbine too. Because I could say maybe there's some heat loss from that turbine, right? But once we do this, we'll get to some kind of symbolic solution, right? So you'll have some equation maybe as a function of delta H's, right? So how do you find H or delta H? So we kind of know how to do this from closed systems, at least in a lot of different cases. So for two-phase mixtures and for superheated vapors, you know how to find these things in textbooks. For subcooled liquids, we know that delta H, if it's a subcooled liquid at the inlet and the outlet, we can assume that delta H is equal to Cp times delta T. This one is tricky that people often forget coming into this second exam, that if you're trying to figure out delta H across an ideal pump, maybe this is a Rankine cycle and you have the pump efficiency, but you can't use the pump efficiency to find the real exit if you don't know the ideal exit. So you can find that ideal exit using this equation, that delta H is the specific volume times the change in pressure across the pump. But it's really important, if you write this equation down, that you tell me that you're using this ideal pump equation. So you're assuming the pump is ideal there, right? So you have to, all these things are like, these equations are like treasures in the chest, right? But you need the key, and the key is the assumption. So if you write down the right equation, but don't tell me why that equation is valid, then you'll lose points for that, right? So you want to, that's sort of the key of engineering, right? Is, the engineer's job a lot of times is to kind of, run through this choose your own adventure that these problems are and get to something that looks like a textbook problem. And the way that we do that is making a series of assumptions. And it's very important for us to track the assumptions that we make so that if things do fail or don't turn out the way that we think that they might, then we have to go back and look at the analysis. And a lot of times it's because of the assumptions that we made, right? So it's really important for you to identify the assumptions that you're making. If we're talking about an ideal gas, then for ideal gases, you can also make the assumption that delta H is Cp delta T, provided that you also tell me that you're assuming that the ideal gas has a constant specific heat. Now, in reality, specific heat changes as delta T increases. So this is a better equation when delta T is small, and the accuracy of this equation goes down as delta T gets bigger. We can also use table A22 for ideal gases to find H. So if I know the temperature of an ideal gas, then I can look on table A22 or A22E if it's metric. If the ideal gas is air, I think it's A23 or A23E if you have other ideal gases. Then you can find the specific enthalpy on those tables for ideal gases. And there you're not assuming that the specific heat is constant. So if you plot those, H versus temperature out there, you'll see that it's a nonlinear function. So we would use, if we were using air, we would say it's a variable specific heat problem if we were using table A22. Basically, anytime you write down an equation that has Cp, right? Two of these equations have Cp, or if they have Cv, like you might use Cv times delta T is delta U, or if they have the expression with K in it, right? So K is the specific heat ratio, Cp divided by Cv. Anytime you use those equations, you're making the assumption that the specific heat is constant. Otherwise, you would have to integrate over temperature as it changes. So if you write down those equations, but you don't tell me you're assuming that the specific heat is constant, then you're demonstrating to me that you don't understand why you're using those equations, right? So you have to tell me that specific heat is constant if you're writing down an equation that has specific heat in it. If we know, say, for example, the delta H across an ideal pump, we would find delta H across the real pump using the isentropic efficiency. Or, conversely, we might also know delta H across, say, a real turbine or a real pump and have enough information to find the outlet across the ideal turbine or the ideal pump. And if I know the power for each one of those components, the real and ideal versions, then I could calculate the isentropic efficiency. So you might get a problem where you're given the isentropic efficiency and maybe you have to find the outlet of a particular component. But you might also have a problem where you're given the outlets of the real and ideal system and the problem asks you to find the isentropic efficiency. Because ultimately it's just an equation, right? So I can give you all the pieces of information except one and then ask you to find that one thing, right? So a good way to look at that, right, is if you have the textbook, you don't have to do every problem in the textbook, obviously. You only have a certain amount of time. But I do think that there's some value in looking at a bunch of textbook questions and spending 5 minutes and kind of mentally plotting out how you would do the problem. Because usually the textbook has a whole lot of problems in it. and they all have different twists. So I find sometimes the hardest thing about an exam is maybe the twist on the problem is a little bit different than what you're used to seeing. So the more problems you look at, the better chance you have not to be kind of caught off guard by a certain twist that you might see on an assignment in an exam. So remember, we made the switch when we were looking at these open systems to move from TV diagrams to TS diagrams. And one of the things that's nice about a TS diagram is if you have an isentropic or ideal turbine or pump, it's a vertical line, right? Because T versus S, and if delta S doesn't change across the turbine, then this will be a vertical line, right? The pressure is dropping across the turbine, but the specific entropy is not changing, right? Just like the ideal pump, the pressure is increasing. That's what a pump does, is it increases the pressure of the fluid, but the specific entropy is not changing, right? And then if you're drawing the real process, we know it has to go to the right if it's steady state, adiabatic, and real, right? Because that entropy generation term will make it so that delta S is positive. So we talked about turbine efficiencies for pumps and for turbines, or isentropic efficiencies for turbines and pumps. The equations are slightly different, but they're both ratios of powers. So the way I think about this is that I always need the bigger number on the bottom, right? And for a turbine, the power that the turbine puts out, that's a benefit to us. And the universe is always kind of, well, it doesn't have like a soul or a brain or anything, but sometimes it feels like it's working against us, right? So the irreversibilities in the system make it so that the real process is worse than the ideal process. So in the case of the power from the turbine, that's a benefit to us. So these irreversibilities, they reduce the benefit to us, which means that the ideal turbine would produce more power than the real turbine. So here, if we're talking about the isentropic efficiency of a turbine, we have the real power divided by the ideal power. If we're talking about a pump, it's kind of the opposite, because the pump consumes power. That's a cost to us, right? So what the universe, or the irreversibilities in the universe, do is make it so the cost that we pay is more than the cost that we would pay in the ideal case. So in this case, the ideal pump consumes less power than the real pump. If you think about this, there's friction in the pump, and because of that friction, you have to put in a little bit more power to get the right amount of energy into the fluid, because you have to put a little bit more power to overcome that friction in the system. These equations, I believe, are both on the equation sheet. We talked about the second law, not just in terms of an analytical equation, but also in terms of these words or these statements. So there's two different ways that we can look at the second law. One is by Kelvin and Planck. So they told us basically, I'm not going to read the words here because I think the words are not super helpful, but they told us that we can take some hot reservoir, transfer heat into a machine, and turn heat into work, right? That's what thermodynamics is. We're turning thermal energy into dynamic energy, right? But the thing is, the engine heats up, right? And if the engine can only communicate with this hot reservoir, it would have to get hotter than the reservoir to dump heat back in here, right? And then the heat transfer is going the wrong way. So in order for us to take heat and turn it into work using a machine, if we're going to run that machine for a reasonably long period of time on a cycle, we have to also have some kind of heat sink, some way of cooling the engine back down. And the consequence of this, because we know that in a closed system, which our machine here is a closed system, the net heat is equal to the net work. So because we need to reject some heat from the engine, that means we can't turn all of this heat that comes in into work. As much as we would like to burn a bunch of coal and turn all of that heat into work, it's not possible, because we do that by making a machine, and we have to keep that machine cool for it to work over time. So Kelvin and Planck told us that we need to have a heat sink. And because we need to have a heat sink, the work that we get is always less than the heat that we put in. There's another way of looking at this, And I think of this Clausius statement as looking at heat going the other way. So we're not really at any local place transferring heat from a cold place to a hot place. But the net result of putting in a refrigerator or an air conditioner is that we cool down a place that's cold and we heat up a place that's hot. Right? And this seems to break what my old heat transfer professor called the zeroth law of thermodynamics, which is that heat always moves from hot places to cold places. And this looks like we're not doing that, but that's because we're zooming out too far. What we do in this machine is we make a cold side that's colder than the cold place. So if you look at the evaporator in your fridge, it's actually colder than the air in your fridge, right? Now the consequence of this is that we also have to have a hot side of this machine that's hotter than the room that you're sitting in, right? So Clausius told us that we can't make a machine like this that looks like it's tricking the universe into transferring heat the wrong way. We can't do that in a machine that's also developing power. We can't even do this if the net power is zero. In order to have a system like this, your refrigerator, you have to plug it into the wall. So in order for a system to do this, you have to add power into the system. Right? So we'll learn as we move on that this system, like a refrigerator, has a compressor in it. Right? So that's why you have to plug your fridge into the wall to run the compressor. We talked about the second law, and this is kind of the elapsed time version, but we don't usually use this version. We usually use this version, which is the rate version. Now, this is much harder to picture than a cup out in the rain, but this first term tells us about how much entropy is being stored in the system. This is not the entropy generation rate. This is the equivalent of if we're getting more mass in our system over time, then we're also probably storing more entropy, right? Then we have some entropy that can come in or leave the system with heat. We have some entropy that can come in or leave the system with mass. But then unlike mass and unlike energy, entropy is not conserved. In fact, entropy is always increasing in the universe. So we know for real processes, this sigma dot term always has to be positive, right? Can't be zero, although that's kind of the ideal case. That's what we can aspire to but never achieve. And we know it certainly cannot be negative. We can't even sort of asymptotically approach a case where entropy is being destroyed if we look at the whole universe, right? So here again, this just talks about what those terms are. So I just said those here. I guess the one note we do want to say here is this Q dot term. This is the same heat transfer that you would use if you did the first law on your system, right? So this is still heat into the system is positive, heat out of the system is negative. This temperature is not a delta temperature, so it has to be in absolute, right? It's got to be in Kelvin or Rankine. But this temperature should also be a temperature that's outside of your control volume. I think ideally, if you look at the definition, it's the temperature on the boundary. But a lot of times we'll use T infinity, or the temperature far enough away from the system that it's not being changed by the system itself. Then we have, entropy coming in and out with the system, and then this entropy generation term, which we know must be positive. Right, so here it says that it's, we can think about systems where sigma dot is zero, even though those can't actually happen in real life. Those, I guess we can, that's the limit of what we could approach, but we can never actually reach that because if it's zero, it's still impossible. It's just impossible in a way that is useful to think about, right? Because it's the best that could possibly be achieved. It's the ideal case. Right? But if it's less than zero, then it's impossible. You can't do it. Right? Common assumptions for this equation could be at steady state, almost always actually in this class. Could be one inlet and one outlet, so the summation signs would go away. If you can write out this equation and make an assumption, the way you draw your control volumes, that it's adiabatic, I would recommend doing that. I think usually when people make mistakes in this equation, it's with this temperature term, by either picking a relative temperature instead of an absolute temperature, or by picking a temperature inside the control volume instead of outside the control volume. But if it's an adiabatic process like you'd see in a turbine or a pump, most times, not all times, then this just becomes 0, right? And then we don't have to worry about what the temperature is, because who cares what you divide it by, as long as the numerator is 0, you're okay. So here we might want to find delta S. So we can find delta S. It's pretty easy. Two-phase and superheated vapors. We're used to that. You look it up in the tables. If it's an ideal pump or an ideal turbine, then delta S is 0. If it's a subcooled liquid, remember for subcooled liquids, delta H is Cp times delta T. For subcooled liquids, delta S is Cp times the natural log of T2 over T1. So here this delta T gets replaced with this natural log of the ratio of temperatures, right? Which you might remember from your math is actually the difference in the natural logs, right? So, but it's okay if you don't remember it. It's just right there, right? So again, because this equation has a Cp in it, so here you'd have to tell me that you're assuming that the specific heats are constant. In this case, because it's a incompressible liquid. For ideal gases, it's tricky. It's tricky to find delta S because you can use tables, right? Now we're used to tables telling us S, but tables for ideal gases don't tell us S. Really, this temperature or this difference in specific entropy can be broken down into two pieces. The change in the specific entropy that's due to the change in temperature of the gas, and the change in the specific entropy that's due to the different pressure across our process, right? So we have a pretty good equation here that describes how delta S changes with the pressure. But if we want the most accurate equation here, right, we would look this part up, how the specific entropy changes with temperature. We would look this up in a table. So if you look on table A22 or A23 if your gas is not air, then you might see this S superscript 0 term and think that that's specific entropy. It's not specific entropy. It's sort of something about how the specific entropy changes because of temperature. So you can get this delta S superscript 0, but you still need to add this part to talk about why specific entropy changes as the pressure changes as well. Now here, this is a nonlinear function, but we've seen that we can kind of, well, I guess it's still nonlinear here because it's a natural log, right? But if we assume constant specific heat, we can approximate this difference by having the Cp times the natural log of T2 over T1 term, same like we did with incompressible liquids. But we still have this pressure term here too, right? Or if it's a closed system, or it's a system where I know the temperature ratio and the volume ratio, then I'd use this approximation D, which again uses a specific heat, but it's CV and not CP. But here I know the temperature ratio and the volume ratio, or the specific volume ratio. So if I'm using constant specific heat analysis, I can use, it's really option B and C here. I don't know why there's an A in front of the tables here. I must have screwed it up. But I can use one of these two options. But if you're using variable specific heat, you have to use this equation here, right? If you want to use the tables and get the most accurate answer. So you have to look up the S superscript values on A22 if the gas is air, or on A23 if it's not air. So we talked about finding delta H for ideal pumps, but I just wanted to show you the derivation again, right? So here, delta H for ideal pumps, right? We have H1 minus H2S, right? This is this isentropic pump. Now, we're sort of often using this assumption that if it's a subcooled liquid in and a subcooled liquid out, you can approximate that as H of this temperature and pressure is approximately equal to HF of the temperature. And since we find that we don't have a temperature change across an ideal pump, if you use that assumption, then these two H's would be the same. And you would get that W dot is 0. That sounds great, but even an ideal pump needs to be plugged in a wall, right? So even an ideal pump is going to consume power. So what we do to get a better answer than that assumption would give us is we remember that the definition of H is U plus PV. So here I take U1 plus V1 and U2 plus P2 all times -1. And I put them into the equation for H1 and H2S. Right now I say that the change in the specific in the specific internal energy is 0, and that the power for the pump is really only driven by this increase in the pressure times the specific volume. I'm also going to assume that the specific volume is approximately constant across this pressure change, so that now my equation just becomes m dot. So this is the specific power, right? But if I want the total power, I'd multiply both sides by m dot, and this is going to be P1 V1 minus P2 V2. But if those specific volumes are approximately constant, then I can pull them out, and I can say m dot times specific volume times P1 minus P2. Usually the inlet to your condenser will be assumed to be some saturated liquid. So that specific volume that you use there would usually be the saturated liquid specific volume at the lower pressure. If it's water, the specific volume is almost always approximately 1 divided by 1,000. If we're trying to find delta H for an ideal gas where the process is isentropic, there's two ways to do this here, but I'm only going to talk about the way to do this with constant specific heat for now. As we move on in the class, we'll talk about the variable specific heat method too. Right? And all three of these equations come from equation A and B here. Right? So this was our ways to find delta S for ideal gases, assuming constant specific heat. So if we set this delta S term to 0, you can get these equations. If I'm trying to find the temperature at the outlet of this isentropic process, and I know the pressure ratio, then I can use this equation. Right? Where here K is Cp divided by Cv. If you're talking about air, it's approximately 1.4. If I know the volume ratios and the pressure ratios, then I would use this equation to find T at the outlet, right? Because I know the volume ratios, and maybe I know one temperature. I'm trying to find the outlet temperature. And if I wanted to compare or equate, I guess, the pressure change to the volume change, then I would use this equation. Although I personally find I end up not really using this equation very much. So if I want to find delta H with ideal gases with variable specific heats, we talked about this a little bit before, but I would use table A22. Table A22 looks like this. It's kind of split in half, right? So the tables only go to here up to VR. When we talk about delta S being equal to 0, we'll talk about PR and VR here, so we don't really have to worry about what these are until after this exam. But if I knew the temperature of an ideal gas, then I would look it up here, right? Let's say it was 220, then I'd see that H was 219.97, right? Or if I wanted the specific internal energy here, or if I wanted S superscript 0 because I was trying to find delta S, then I would put this in, right? And I could get, if my other side was at 490, then I could get S superscript 0 here, and I'd get that delta S superscript 0, which is kind of the change in the specific entropy because the temperature is changing. So that's kind of how we use this table. Don't worry too much now about PR and VR. These are things that we'll talk about more as we move along in the class. So if you remember when we talked about ideal gases, these are the reduced pressures and the reduced volumes. So basically the pressure divided by the critical pressure, or the specific volume divided by the critical specific volume. If you look on the equation sheet, we tried to sort of arrange it in a way that was useful. So here you have some equations, isentropic ideal gas equations. So if your process is isentropic and your working fluid is an ideal gas, you can use these equations. Now for this exam, we're only going to focus on these three equations here. But if you knew the pressure ratio, it's equal to the reduced pressure ratio. And if you knew the volume ratio, it's equal to the reduced volume ratio. But we don't have to worry about doing that because we didn't really talk about that before the exam. But that's why we need those things. So we're going to focus more on these cases where we're assuming specific heat is constant as we move into the second exam. So we also talked about integrating things together to make thermodynamic cycles, right? So a cycle is just a bunch of systems in a row where basically we start and end at the same place. We talked specifically about these Rankine cycles, right? And a Rankine cycle is a heat engine, so really we're trying to produce power. So it's a turbine that we want to run. So we start off with some high pressure, high enthalpy steam. right? It's going to run through our turbine, and that's going to reduce the pressure. Now, the whole rest of this cycle is just to get back to the inlet of the turbine. So we condense that steam into a liquid because it doesn't take much power, comparatively, to increase the pressure of a liquid. So now we're up at the right pressure to get into the turbine, but we have a liquid and we want to run vapor through our turbine, so we have to boil it. And this is why we add heat. Now we have steam again and we can expand it through the turbine. So that's kind of what a Rankine cycle is in its most basic form, right? So in this 4-component cycle. So that's a heat engine, right? Where the energy benefit is producing power and the energy cost is burning something or doing some other exothermic reaction like a nuclear reaction to generate heat. We also talked about heat pumps. So this is a picture of both a heat pump and a refrigerator. We don't have to do this cycle yet, but we talked about this kind of in the macro sense, where in these cases, if I'm a refrigerator, my energy benefit is removing heat from the cold place. And if I'm a heat pump, my energy benefit is adding heat to the hot place. And in both cases, my energy cost is that I have to plug that thing into the wall to run my compressor, which is going to be the net power. So if we have a thermodynamic cycle, like a Rankine cycle, I think that there's a series of things that we should do, right? So the first is define this characterization parameter. So it's either going to be a thermal efficiency or a coefficient of performance, which is what gamma and beta are. So here we'll say that it's the energy benefit divided by the energy cost, no matter what kind of cycle it is. Then we'll do conservation of mass on all the elements. We'll do the first law on all the elements. We'll do the second law if we need to on different elements. But then we'll get a bunch of equations that maybe have delta S's or delta H's in them. And to figure out a numerical answer, we have to ask ourselves, what's the working fluid? Right? How do I find delta H? Right? And then we can fix all the states. So if we have our state table, we can keep putting in information for the enthalpies. And then when we get all of that, we can put those numbers for enthalpies back into the symbolic equations we get from the first law, and we can figure out things like the power from the turbine, the power consumed by the pump, the heat in at the boiler. And if we know those things, then we can find the thermal efficiency of our Rankine cycle. And if we know the actual thermal efficiency, then we can compare it to the Carnot efficiency, right? So if we can do all this, but there's a lot of steps, right? So I'm not always great at remembering a whole bunch of steps. So what I really want to do is here, I want to know the characterization parameter. So what's the energy benefit and the energy cost? In a Rankine cycle, the benefit is net power and the cost is heat in. Then I want to know if the system is open or closed, or if the processes in the system are open and closed, because that'll tell me which version of the first law and the second law that I need to do. And then the third thing that I want to know is what's the working fluid. So if I know what the working fluid is, then hopefully I'll be able to remember how to fix the states. And once I fix all the states, I basically just go back to what I had here and get answers for the symbolic solutions that I already derived. So that's kind of how I think about doing cycles. As we move past this second exam, we just go cycle after cycle and bang them out, right? So this is our process for all of those cycles, including the Rankine cycle that we just learned. So real characterization parameters, if I'm talking about thermal efficiency, it's going to be net power divided by heat in. If it's coefficient of performance for a refrigerator, the energy benefit is the heat removed from the cold side. The energy cost is the net power. And if it's a coefficient of performance for a heat pumps are almost exactly the same as refrigerators. It's just our perspective is different. We're sitting on the hot side. So our energy benefit is we're trying to heat up the hot place. So the difference here between refrigerators and heat pumps is that in a refrigerator, we're interested in the heat transfer on the cold side. And in the heat pump, we're interested in heat transfer on the hot side. If I have a Carnot efficiency, what I can do is remember that for this closed system, if I zoom out far enough, even in a Rankine cycle where the individual components are open systems, I can zoom out far enough and think of it as a closed system because all these systems are sort of chained together. And I know that net power in a closed system is equal to net heat. So net power is heat in minus heat out. And if I have an equation that's a ratio of heat transfer terms, then if it's ideal, I can change it to a ratio of temperatures. So my Carnot efficiency is going to be given by 1 minus T cold over T hot. So your Carnot efficiency is the best efficiency you can get. So let's say your Carnot efficiency for a particular heat engine is 55%. But you have a salesperson telling you that their efficiency in that case is 60%. They either are trying to mislead you or they don't know what they're talking about, because you know that you can't do better than the ideal efficiency, and 60 is higher than 55. For coefficients of performance, we do a similar process here. It's just now our network is on the bottom instead of the top. So again, we have this ratio of heat transfer terms, which only in the ideal case we change this to a ratio of temperatures. Right? Notice that a lot of these temperature ratios are not delta T's. So absolute temperatures are good to use for these equations. So here we can do this. We can find the best coefficient of performance. Now, coefficient of performance is a little bit funny. It's not an efficiency. So efficiencies run between 0 and 1, or 0% and 100%. Coefficients of performance are going to generally be larger than 1. So that's why we don't call them efficiencies. So our coefficient of performance for a heat pump looks almost the same here as for a refrigerator. But again, on the heat pump, the benefit is on the hot side. So here we want T hot in the numerator, whereas in the refrigerator, we're trying to cool down the cold part, so it's T cold in the numerator. Other than that, they're the same. My advice always is, if you're using temperatures in these equations, to always use absolute temperatures, even in these temperature control cycles where the denominator is still delta T. If you use absolute temperatures, if you put them in Rankine or you put them in Kelvin, you're never going to get it wrong, right? Or at least you won't get it wrong because the units are wrong. Whereas, so if you just automatically default to that, it's one less thing you can mess up, right? So Rankine cycles in particular are this chain of 4 components: the turbine, which is the workhorse, then the other things that get us back to the turbine, entrance, which is the condenser, the pump, and the boiler. It's important for you to know how to draw these TS diagrams. You could certainly get a long answer problem where you have to do a Rankine cycle, and part A is draw the TS diagram. So for a Rankine cycle on a TS diagram, the whole thing about a Rankine cycle is we're going back and forth across the vapor dome. So you have to draw a vapor dome. And then you have a low pressure line and a high pressure line. And you can see the turbine, you go down. The condenser, you go across. The pump, you go up. And the boiler, at constant pressure, you add heat, so the temperature goes up. And then you get back to the turbine, so it's a cycle. Right? Remember, the ideal turbine is vertically up and down, but the real turbine goes down and to the right. The ideal pump is vertically up and down, but the real pump goes up and to the right. We get power out at the turbine. The condenser rejects heat. Pump or work goes in at the pump, and heat goes in at the boiler. When you draw a TS diagram, you don't have to draw these lines. I like to draw power as a straight line, heat transfer as a squiggly line. But I like to draw these lines because just from looking at this, I know that heat's coming out at the turbine. So that's work out. Work out is positive. Heat's going into the cycle at the pump, or power's going into the cycle at the pump. Power in is negative. Heat's coming in at the boiler. Heat in is positive. Heat's coming out at the condenser. Heat out is negative. So just drawing this, I know what the signs are of the different processes, and I also know what the major term that I'm interested in each of these processes. So I think it's helpful not only to draw the cycles, but to also draw the sort of dominant energy piece. But you don't have to draw the power and the heat transfer on a TS diagram. So heat engines, right? So for the real heat engine, right? So Rankine cycles are heat engines. For the real heat engine, you want net work divided by heat in. For the Carnot heat engine, 1 minus T cold over T hot. We know that the actual thermal efficiency should be less than the ideal thermal efficiency. Another way that we can sort of characterize these things is with a backwork ratio. So the backwork ratio kind of acknowledges that the pump is the first the pump is the first consumer of the power plant. So this says how much of the power that we generate in the turbine goes to just continuing to run the cycle. This is one of the things that we like about Rankine cycles, is that the backwork ratios tend to be low, maybe around 1%. We know first law for open systems. So in these Rankine cycles, typically we'll say that everything is at steady state. Everything is one inlet, one outlet. We'll neglect kinetic and potential energy changes. For each component, we'll say it's either adiabatic or passive. we'll say that there's no friction or heat losses through the lines. And if we do that, we'll get this equation, that the turbine power and the pump power are going to be m dot times h in minus h out, that the condenser and the boiler heat transfer rates are going to be m dot times h out minus h in. Now here we then have to say, okay, what's the fluid? How do I get these delta H's? And I think the trickiest one here is going to be the pump, because remember, the delta H for the pump is going to be V times delta P. Right? We also know the signs here. The turbine power should be positive. The condenser heat transfer rate should be negative. The power consumed by the pump is negative. And the boiler heat transfer rate is positive. Then we got to say, what's delta H? And we can think about how to find that. So that's, I know I took a little bit longer than 50 minutes here, but that's kind of my overview of what we're supposed to know going into this second exam. So I won't keep you any longer, but if people have questions, I'm happy to stick around for a little bit to answer them.
I actually had a question about this week's homework.
Shoot.
So for one of the questions, I think it's question like 6.7. We're only given in the problem statement one, because it's one of those questions where there's a case A, B, C, and D, and you have to find the unknown. And we're only given A. Do you want us to find B as well? Because I believe in the solutions there's something for B as well, but I only have information for A.
Oh, so you're saying I only photocopied part A?
Yeah.
Okay, that's fine. Just do part A then.
Okay, thank you.
You're welcome. Any other questions? All right. Well, we will start with new material on Wednesday, and then the exam will be on Thursday. So thank you for coming, and I will see you all on Wednesday. Take care.